This is the fourth section of the constant acceleration chapter, chapter 9, and here we're going to be looking at some more constant acceleration formulae. Now, we've already derived two constant acceleration formulae, and that's this one here, v equals u plus at, and s equals u plus v over 2 times by t. And we got these just by looking at the gradient of a line on a velocity time graph, and also by looking at the area under a line on a velocity time graph, straight line because it's constant acceleration. Now I'm going to label these equations 1 and 2 here, and then I'm going to derive these equations down here simply by taking equations 1 and 2 and eliminating a particular letter from them. We saw from the previous section that there were times where we had to use a value that we just calculated, and it would be useful to have another equation where, if you've got three unknowns, we can use those without having to use a value that we've previously calculated, just in case it's wrong. So the first thing we're going to do is this. We're going to take what I've labeled equation number 1, substitute it into 2 to eliminate t. So what that means is I'm going to take the v equals u plus at. I'm going to rearrange it to make t the subject. So I have v minus u equals at, and then I can divide both sides by a, and I've got t equals v minus u over a. Now what I'm going to do is substitute it into this equation here to get rid of the t. So where I have t, I'm going to put this instead. So here comes the substitution. I now have s equals u plus v over 2 times by, so t we substitute for this, and we get v minus u over a. Now, if I just rewrite this equation as v plus u over 2 times by v minus u over a, you'll notice that this is the difference of two squares. So if I multiply this all out, I will get s equals v squared minus u squared all over 2a. Just multiplying it out like that. Let's multiply both sides by 2a, so we'll get 2as equals v squared minus u squared, and we can rearrange that to make v squared a subject, and we'll get v squared equals u squared plus 2as. And what we've done is we've derived this formula here, v squared equals u squared plus 2as. That's in the formula book. So by doing this substitution here, we get this formula. Okay, right, now what we can do is do the second thing here, which is to substitute equation 1 again into 2, but this time to eliminate v. So we're going to make v the subject of this. Well, it's already the subject of that, so there's no rearranging required. V equals u plus at, and then I'll substitute that into equation number 2. So where I've got v, I'll replace it with u plus at. So I'll have s equals u plus, and then v becomes u plus at, and that's all over 2 times by t. Then what we'll do is we'll just multiply at the top of that fraction and add everything together. So we'll have 2u plus at. Now that's all going to get times by t over 2. Let's multiply that out. So I'll have 2ut plus at squared all over 2. That's the same as s equals 2ut over 2 plus at squared over 2, because they've both got the same denominator, and that will give us s equals ut plus half AT squared because it's over 2. So what we've done now is we've derived this SUVAT formula here. Again, by taking the same two starting equations, but just changing what letter that we're eliminating. Okay, so there's our fourth SUVAT equation. Now these are all in the formula book. You don't need to memorize them, but the more you use them, the more likely you are just to know them off the top of your head, and that's the best way to be able to use these. And the next one, we're going to substitute equation number 1, this one, into equation number 4. So now we're going to call this 3 and 4. So we're going to substitute this one into this one here, but to eliminate u. So we start with v equals u plus at. We're going to rearrange it to make u the subject. So we'll have u equals v minus at. And then we're going to substitute that now into this equation here, equation number 4. Right, so if we do that, we'll have s equals, so u now gets replaced with v minus at. So it's like ut plus half at squared. From there, we'll multiply the brackets. So I'll have vt minus at squared plus half at squared. And then from there, we'll just get vt. So if you've got like an at squared and you add half an at squared, you're going to end up with minus half at squared. And this is our third and final substitution to create our fifth SUVAT equation. So in all the questions that we do, when we see what knowns we've got, and if we're not solving simultaneously, there'll be at least 3 knowns, then we can use that to pick out which SUVAT equation we need to use. So you want to practice really saying, right, I've got these sets of letters, which one of these am I going to use? And if you can get used to doing that quickly, that will save you a lot of time. Right, so in each of these examples, I've put the SUVAT equations up at the side here, just as a quick reference. So it's a bit like, you know, if you're doing an assessment or an exam, you will have the formula booklet maybe opened at that page, just in case you need a quick reminder of the SUVAT equation. So we've got a particle is moving along a straight line from A to B with constant acceleration, 5 meters per second. Okay, so let's just underline that. We've got acceleration. The velocity of the particle at A is 3 meters per second in the direction AB, so that looks like the 3 meters per second is our initial velocity. The velocity of the particle at B is 18 meters per second, so maybe that's our final velocity, V. Find the distance from A to B. So we start all of these the same way. Start by writing out SUVAT. Now what do we know? We know the acceleration is 5. The velocity at A is 3. There's our initial velocity. The velocity at B, our final velocity, is 18, and we want to find S. So we're looking for one of these SUVAT equations here that has S, U, V, and A. So we can forget about all of the ones which have got T in. That's the first 2 and the last 2. So that might be a quicker way of doing it. This is the only one we can use that doesn't have T in it, so we'll write down the equation that we're using. V squared equals U squared plus 2AS. And now we just substitute in the values. 18 squared equals 3 squared plus 2 times A, which is 5, times by S. And it's just a matter of working out what this is. So that will be 18 squared. Let's work out what that is on my calculator. 324 equals 9, 3 squared, plus 10s, 2 times 5s, that's an s there, not a 5. So then we will take away 9 from both sides, then divide by 10 to get s, and what we will have is s equal to 324 minus 9, that's 315, divided by 10. That's going to be 31.5, and that will be meters. Okay, so here we've got a particle moving in a straight line with constant deceleration, 4 meters per second. Okay, so deceleration, so I'm going to be using a -4. At time t equals 0, so basically at the start, the particle passes through point O with speed 13 meters per second. So this is probably what's going to be our U, traveling towards a point A, where OA is 20 meters. Okay, so that'll probably be our value of S. Find the times, and notice it says times, not time, when a particle passes through A. So we're expecting 2 solutions to our answer. So first of all, I'm just going to draw a diagram so we can see what's going on. So we've got this point O, and when t equals 0, it passes through this point, and its speed is 13 meters per second. Then we've got this point A that it passes through, and we know the distance to get to point A is 20 meters. Now, because it's decelerating, probably what's going to happen is it's going to slow down until it comes to a point probably beyond A where it stops, comes to 0 velocity, and then it's actually going to change direction. If something continues decelerating, it actually stops and then changes direction. So that's why it says time. So imagine it gets to this point here, somewhere there, stops, and then returns back this way. Okay, so first step is SUVAT. So S is 20, U is 13, V we don't care about, A is -4, and we want to find T. So the equation that has S, U, A and T is S equals UT plus half AT squared. Always write the equations out. As you use them, it will just get used to remembering them. So we now substitute in the values. 20 equals 13t plus half A, that's -4, t squared. Now you notice what we've got here is a quadratic, so I expect there to be 2 solutions. That's why it says times to get 2 values for t. All right, so 20 equals 13t, and that will be minus 2t squared. I'll rearrange it so it looks like a nicer quadratic. So I've got 2t squared minus 13t plus 20 equals 0. So I can solve this by factorizing, using the quadratic equation, or using my calculator. I'm going to use the quadratic equation. You may not necessarily spot that this can factorize. So quadratic equation always works. So t is going to be equal to minus b, so minus b, which is -13, plus or minus the square root of b squared, which is -13 squared, minus 4 times a times c, all over 2a, so 2 times 2. Right, let's see what we get from that. So that will be 13 plus or minus the square root of 169. 4 times 2 is 8. 8 times 20 is 160. All over 4. So from there I will get t equal to 13 plus or minus, now 169 minus 160 is going to be 9, and the square root of 9 is 3. So 13 plus or minus 3 over 4. So what does that give us for our values of t? Well, 13 plus 3 is going to be 16. And 16 divided by 4 is 4. So that's one value of t. And then 13 minus 3 is 10. And then 10 over 4 is the same as 5 over 2. So 5 over 2, or 2.5. Okay, so here we go. These are the times at which the particle passes through A. So basically what happens is after 5 over 2, or 2.5 seconds, it passes through A, and it stays beyond A for another 1.5 seconds, and then at 4 seconds it gets to A, and then it carries on actually accelerating in a negative direction. Okay, part B of this question says find the value of t when the particle returns to O. Right, the particle will return to O when the displacement of that particle is 0. Yeah, so we get back to displacement here, not distance. It may have traveled a distance much more than 0, but its displacement is 0. Right, so we still have the same initial velocity. V we don't care about. A is still -4. And t is the value we want to find. So again, an equation that has SU, A and T, S equals UT plus half AT squared. And we'll just substitute in 0 equals 13t plus half times by -4 times by t squared. So that will give us, if I just do this, 13t minus 2t squared. Now that's easy to factorize because that'll be 2t squared minus 13t equals 0. So that'll just be a t outside the bracket, and then a 2t minus 13 equals 0. So that will give us t equals 0. Well, we expect that. It will be at the origin at the start, but when it returns to, it will be the other value of t. And we'll get that value of t by working out when 2t minus 13 equals 0. So 2t minus 13 equals 0. So that gives us 2t equals 13. T equals 13 over 2, which you could leave as 6.5 seconds for the time that it returns to O. So we'll just highlight that before we move on to the next example. Particle P is moving on the x-axis with constant deceleration to 0.5 meters per second squared. At time t equals 0, the particle passes through the origin O, moving in the positive direction of x with speed 15 meters per second. And part A, what we need to do is to find the time between the instant P first passes through O and the instant when it returns to O. So like the previous one, we're just going to do like a little diagram, show what's going on. So it's moving in the x-axis, direction x-axis like this. And its deceleration is 2.5 meters per second squared. At t equals 0, it passes through this point O, the origin, and it's moving in the positive x direction, that direction, and its speed is 15 meters per second. So here we'll put 15 meters per second when it passes through O. Let's just add the minus to the deceleration. So like the previous example, it's slowing down, slowing down, slowing down, gets to 0, and then reverses direction. So let's write down our SUVAT. So we want to find when it returns to the origin, when the displacement is 0. U is 15. We don't know what V is. A is -2.5. And T is what we want to find. So SUAT is S equals UT plus half AT squared. So it's going to be 0 equals 15t plus half times by -2.5 times by t squared. So that is 15t, and then half of -2.5, that will be, I'll write that as 5 over 4 I think, or 1.25, so -1.25 t squared. This should be an easier one to factorize. So we can write it like this: 1.25t and then minus 15 like this equals 0. So basically I've just moved both these terms to the other side, so that becomes positive, that becomes negative, and then factorized it. So from this, either t equals 0, which we know that's when it first time when it passes through it, but when it returns to it, that will be when 1.25t minus 15 equals 0, or 1.25t equals 15, which will mean t equals 15 divided by 1.25, which gives us 12. So it will return to the origin after 12 seconds. Now in part B, it says we want to find the total distance travelled by P during this time. Now with this, we can't work it out by just saying, okay, let's just look at when the displacement is 0, because displacement is not the same as distance. What we need to do is to find out when this particle changes direction and then starts to return back. So let's call the point at which it changes direction, let's just call it C for change, C. So this is the point P changes direction. So it gets to a velocity of 0 and then it changes direction. Now we can work out this displacement here to this point and then we just double it. So let's say, for example, it travels 20 meters before changing direction. Then the distance travelled during the time that it returns to the origin is going to be 20 there and 20 back. That will give us 40. So we have to do it this way. If a particle changes direction, we've got to work out the displacement for each part of the journey and then add them together. So we're going to work out how far it is to this point when it changes direction. Whatever that distance is, it travels the same distance back, so we just double it. So what we need to do for part B when we write out SUVAT is we want to find the value of S when V equals 0. It changes direction at that point in time when the velocity is 0. It stops moving for an instant. Think about when you throw something up in the air and it comes back down again. At the very top of the motion of that particle or ball or whatever it is, the velocity for a split second is 0 as it changes direction. So you might want to remember that when something changes direction, the velocity is 0. Right, let's finish this off. So the initial velocity is still 15 and the deceleration is still negative 2.5. We're not worried about t, so we're looking for an equation that has S, U, V and A in it. And that's going to be the V squared equals U squared plus 2AS. Remember, that's the only one that doesn't have t in it. So we'll write that down, V squared equals U squared plus 2AS. So we've got 0 squared, now we just substitute. U is 15 plus 2 times negative 2.5 times by S, so that's what we need to find. So remember, that's an S here, not a 5. So that will give us 0 equals 225, and then the 2 times by negative 2.5 will be negative 5S. This is where we've got to be really careful. Got an S and a 5 right next to each other. Right, so that will give us 5S equals 225. So that means S is equal to 225 over 5. Let's work that out. 225 divided by 5, which is 45. So what does this tell us? This tells us that the distance from here to here, from our origin to C, is 45 meters. I'll put up my diagram. 45 meters from there to there. So I'll just write down OC equals 45 meters. Now that's not the final answer, because during the time that we're talking about, the total distance is going to be there and back again. So we need to times it by 2. Okay, so 2 times by OC gives us 45 times by 2, which is going to be 90 meters. Now that is the total distance that's been traveled during this time. So the total distance is 90 meters. I'll just highlight that before moving on. Total distance is 90 meters. So you should now be able to do exercise 9D on pages 145 to 146. Just do a quick recap here of our SUVAT formulae. So 2 we had from before, V equals U plus AT, and this we had before when we looked at section 1 on the constant acceleration formulae, and we were able to derive these 3 using those 2. So V squared equals U squared plus 2AS, S equals UT plus half AT squared, and then S equals VT minus half AT squared. Okay, and if we were to number them 1, 2, 3, 4 and 5 and actually write out SUVAT like this, we could probably create a little table to show, okay, which actual values are given by each equation, and we'll just put like little ticks in this. So we'll start with equation number 1. So equation number 1, that uses U, V, A and T. So U, V, A and T. S equals U plus V over 2 times by T. That doesn't have the acceleration in it. So that has these in there, those 4. The third one, that's the only SUVAT that doesn't have T. So that has those 4. The next one doesn't have V in it, equation number 4, so no V in that equation. And then the last one doesn't have U in that equation. So you can see this basically covers all the different combinations that are required to answer a question where we're dealing with constant acceleration.